Hey guys, Professor Sweeting here, and we're going to continue where we left off in this video with the edge coloring problem. So in the last video, we were just discussing a few graph families for which the edge coloring problem kind of has a predictable solution. So graphs in a graph family share some kind of similar pattern or underlying structure, and because of that underlying structure, we can know what the edge chromatic number would be of a member of this family, or even, in certain cases, have an algorithm for efficiently and effectively finding a minimal coloring of the edges. So that's the case with the cyclic graph family that we looked at, which are all graphs that are connected and such that each of their vertices has valence 2. And it's also the case for bipartite graphs, right? So for cyclic graphs, we either have the edge chromatic number being 2 if it has an even number of vertices, and it's 3 whenever there are an odd number of vertices in the cyclic graph. For bipartite graphs, we have that the edge chromatic number is the maximum degree of the graph. So recall that the maximum degree is the largest valence of a vertex in the graph. All right, and so in the last video, we also saw that even if we know this value, right, so we kind of suspected that the edge chromatic number of elements of this graph family was 2. I didn't formally prove it, but rather I just we looked at a few examples and just extended the pattern from there. But these are results that actually hold true and are proven by other people in other literature, but that's all beyond the scope of this class. But we saw that even if we know this value, it's still difficult to take those colors, right, that we know we need to use, right, the number of colors / labels that we know we need to use to be able to label every edge or color every edge so that adjacent edges, right, edges sharing a vertex have different colors, right? Even if we know that, to do that is still a difficult task, as we saw here, right? So I tried using 3 colors and I ran into a problem as I was coloring, which required me to use 4, right? But we see here we were able to make do with just 3, as should be the case, right? So the bipartite graph family is, for this family of graphs, there is actually a well-known algorithm which would help you systematically get this coloring for any member of its family, right? So that's just something to keep in mind and is relevant for the problem that we'll talk about later. So we're going to continue by discussing the family of complete graphs, which we should all be well aware of, and trees, which we all should also be well aware of, because we studied these extensively when looking at Kruskal's algorithm and the problem of minimum cost spanning tree, and then also for traveling salesman problem, right? We looked at complete graphs in Hamiltonian circuits. So for the complete graph family, I'm going to state a result without proof, and that is that the edge chromatic number is equal to the maximum degree of a complete graph if n, which is to be its number of vertices, is even, and it is 1 more than the maximum degree if n is odd, right? So that is the result for complete graphs. So for graphs in this family, we know what the edge chromatic number is, and there are algorithms out there, which we're not going to discuss, for actually finding a coloring using that minimum set of colors, right? So here are just some examples. We've looked at this graph. So we've looked at this graph before, and we saw that it's a complete graph with 3 vertices. So this statement, and it has an odd number of vertices, right? So this statement says that its edge chromatic number is going to be 3, right? So 1 more than maximum degree. The maximum degree is 2 in this case, so it's 3, right? And we saw that. And then for the complete graph with 4 vertices, this result states that its edge chromatic number should be the same as the maximum degree, which it is. So edge coloring, we colored this graph with 3 colors, right? And had no adjacent edges sharing the same color. So this is the edge chromatic number, and it's equal to the minimum or maximum degree of the graph. So that follows along with this result, which is stated for all such members of this family. And then, lastly, we have a complete graph with 5 vertices. This statement says then that since the maximum degree is 4, it's a complete graph, it has an odd number of vertices, that the edge chromatic number should be 1 more than the maximum degree, which is 4 in this case, so it should be 5. And we see that. So this is a coloring that is achieved with only 5 colors, right? So these two colors are different. This blue and this blue are different from this blue and that blue, right? And so if it's difficult to tell, I also included labels there for each of the colors. All right, and then for trees, we have another result that I'm going to state without proof, that the edge chromatic number of a tree is equal to its maximum degree. So again, the proof of this is beyond the scope of this class, and it suffices just to know this result, right? And why is that the case? Well, knowing, or having as that foundation results for each of these graph families is useful, because sometimes when you're looking at a problem and it boils down to finding the edge chromatic number of a graph, if that graph looks like any of the graphs from these families, we know right away, without any amount of work whatsoever, what the edge chromatic number is, and would maybe even have an algorithm for finding a coloring. So so this is the result for trees, and just to reiterate, trees are connected graphs such that there exists no cycles, right? So cycles meaning, so if we add this edge here to the graph, this would be a cycle, and therefore this wouldn't be a tree. Yes, so for such graphs without that, right, we have that the edge chromatic number is equal to the maximum degree. Okay, so to finish this video, we are going to look at an example of a real-world problem that can be solved via edge coloring. So this isn't going to be as interesting as the problem that we had discussed for the vertex coloring problem with the scheduling of tasks and those conflictions. So in that problem, right, this is not this problem. I just want to reiterate that problem, right? We had that if we had a certain number of tasks that needed to be completed, right, say in this case 4, okay, and we drew a graph that had as its vertices these tasks, and the only information we had was that these tasks, which all take the same length of time to complete, certain tasks couldn't be worked on at the same time as others, right? And we wanted to know what the minimal completion time was, right? So if there was an edge, we drew an edge in this graph connecting the vertices of tasks that couldn't be worked on at the same time. So for example, if the graph that we ended up with, that we construct for that problem looks like this, then we know that we have 4 tasks, and task 2 can't be worked on at the same time as any other task, but each of the other tasks can be worked on at the same time as one another, right? So this is what that graph would represent. Well, in this case, we had that the vertex coloring number, right, amounted to the minimal completion time for all tasks if they all took the same length of time, right? Because if we can color tasks the same color in this graph, right? And not have them. So if we can color as part of a valid minimum coloring, vertex coloring, vertices in this graph of the same color, that means that they can be worked on at the same time, right? So those groupings of colors correspond to groupings of tasks that can be worked on at the same time. So if we have enough processors to work on all of those tasks at the same time, then we could complete all tasks in the amount of time it takes in the number. Okay, so then if we had unlimited processors at our disposal, we would only require as many units of time to complete all tasks as there are different colors used, right? So we can, for example, so I just wanted to restate this problem because I found it very interesting, and it's going to be on your quiz for this week. So, then if we had our processors to schedule these tasks, right, and we had enough of them, then any of these that are the same color can be scheduled at the same time. And those that aren't have to be scheduled at a different time. So total length of time is equal to chromatic number. All right. So the problem that we're going to be looking at, so this was using vertex coloring, right? The problem that we'll be looking at that uses edge coloring is completely different, but it's still a scheduling problem, right? So open shop scheduling is a problem of scheduling production processes in which there are a set of objects to be manufactured. Each object has a set of tasks to be performed on it in any order, and each task must be performed on a specific machine, preventing any other task that requires the same machine from being performed at the same time. So the question is, in this situation, is there a systematic way to create a schedule for all tasks to be completed, right? So can we come up with something like, kind of like if we have machine 1, machine 2, right, and machine 3. So what should be working on, so how do we come up with a schedule of the sort like this? So this should be working on object 1, right, at this time, for this time interval. So we have these time intervals. So I think an assumption here that I didn't mention in the general statement of the problem, but I did mention in the specific example, is that each of these, the amount of time it takes each machine to complete its task on an object is the same, right? So this is like time interval 1, time interval 2, right, so on and so forth. So how can we, right, come up with some kind of scheduling, like, so that each machine is only occupied with one object for the time interval, object 1, object 2, object 3, so something like this, right? So how do we make this scheduling? How can we effectively assign the scheduling so that there are no conflicts? And conflict in this case would be that a machine can't work on the same task at the same time. So if a machine, or the same task on 2 different objects at the same time. So that's the only restriction. So how do we create such a schedule that tells each machine what object they should be performing a task on what time interval, right? So how do we come up with something like this? And the answer is by using edge coloring, by representing the problem as a graph and using edge coloring. But let's see, how do we make that connection? Well, let's look at a specific instance of this problem, right? So say we had 3 cars at a dealership that needed maintenance. So each car is to be washed, have its tires rotated, and oil changed. Say the dealership has a specialized machine for each of these tasks, right? Say a drive-through car wash, a pneumatic wrench, and a car lift. And each task took the same length of time to complete, say 30 minutes. So we can represent this problem as a bipartite graph where the vertices in one column correspond to machines and the vertices of the other column correspond to cars, and the connecting edges represent the completion of a specialized task on the destination car by the source machine. So let's draw that here. Okay, so this is how we could maybe start to represent the problem. So this would be car 3, car 2, car 1, right? And this could be the car wash, right? This can be the car lift, and this can be the pneumatic wrench. Right? And then the car wash needs to perform its special task on each of the cars, right? So the edges represent completion of a specialized task by the source machine on the destination object, right? So the car lift needs to operate or perform its specialized task on each car, each object, and the pneumatic wrench needs to do the same for the, so that would be for the tire rotations, okay? So now, all right, furthermore, we can reserve a color or label for a particular time interval, right, which we then assign to an edge. So for example, one color we can use to represent the first 30-minute interval, another color we can use to represent the next 30-minute interval, and so on. Since no machine can be working on two cars at once, finding a specific schedule, like so, amounts to finding an edge coloring of the graph. Alright, so let's see. Okay, so we can use different colors to assign to each edge, right? And by assigning a color, say we can use green, or this label A, to represent completion of task, or assignment of task. Let's just say to the first interval, first 30 minutes, right? Remember, each task took 30 minutes to complete. And then we can use this pink. We can assign that to a label, the completion of a task, to represent the second 30-minute interval. And then we can use maybe this yellow here to represent the third 30-minute interval. Okay, so coloring these edges is assigning a completion of a task to a certain time interval. I hope you can see that, right? So if we colored this edge right here green, that would mean that we should be running car 1 through the car wash during the first 30-minute interval. Now, why can't these edges be the same color? Well, we can only have, part of the assumption for this open shop scheduling problem is that each of these machines can only work on one object at a time. Okay? So you can't have these two edges be the same color, because that would imply that during the first 30-minute interval, the car wash is working on both cars. So what we're looking for in this problem, right, so coloring this color green means that in our kind of scheduling here, if we have each of the machines and we're trying to schedule their timeout, car wash, car lift, pneumatic wrench, right? And this is the first 30 minutes. This is the second 30 minutes. And this is the last 30 minutes. Okay, and we're trying to designate, that would mean that coloring this color would mean that the car wash is working on car 1 during the first 30 minutes. So filling out this diagram here amounts to, in accordance with the condition or the restriction that a machine can't be working on two different objects during the same time interval at the same time, right? So filling out this scheduling amounts to finding an edge coloring of this bipartite graph. I hope you'd all see. So remember, for this bipartite graph, the vertices in the left column are the machines, the vertices in the right column are the objects that are being having tasks completed on them, and then an arrow, right, an edge represents the completion of that specialized task by this machine on an object, right? And so, yeah. So filling this out, this scheduling out, amounts to finding the edge coloring of this graph. So, like I had mentioned before, for graph families, there exist, like for example, bipartite graph, there exist well-known algorithms that we can use to systematically find a way to get a coloring here, and therefore a scheduling in the end, right? So, we saw that that's not always easy. So we know that for this bipartite graph, and it should be pretty obvious, that we should be able to make do with 3 time intervals, okay? Because we only need 3 colors for our minimum edge coloring, and that was a result that's known for bipartite graphs and that we'd stated, right? But actually getting one we saw is a rather difficult process. So there would be an algorithm, which I'm not going to state, that we could just employ to just color this and therefore get the scheduling, right? So, yeah, and like I said before, and as we had seen when I first introduced bipartite graphs, or the edge coloring with respect to bipartite graphs, that can be rather difficult, okay? So, all right, let's see. Okay, I guess, I mean, I don't know. I don't think I'll actually finish this coloring. The point of bringing up this problem was just that, you know, to see the connection between edge coloring and something maybe useful, right? Since I don't have the algorithm, it doesn't really make sense to finish the coloring. So, all right, so in the next video, we'll end our discussion of coloring problems with the face coloring problem, right? And in that video, we're also going to discuss, I think, I'm not sure yet, I haven't decided, a general algorithm for solving these colorings. It's very inefficient and it's very tedious, but I think it is systematic in that it can be applied to any given graph to get a good, and any component to get a minimum coloring, but I think it's just extremely inefficient is the issue with it. So the algorithm that you'd use for bipartite graphs and maybe specific graph families would be far more efficient and far faster. Right? I actually will finish this. I'll try to finish this coloring here. So I'm not using the algorithm that's meant for bipartite graphs. I'm just trying to see if I can get something. So let's do that one, this color, that one, this color. So A, and then let's see. As you can see, it's not a trivial process by any means, like getting this coloring and equivalently filling out such a schedule, right? Okay. Let's do this in yellow then. Wait, did I actually do this bipartite graph? No, I did 3 too. Okay. We'll do that. And then maybe this one here. And we're already out of luck because I'd have to, coloring that yellow, that was the wrong move, because then I'd have to color this pink if I'm reusing my 3 colors to color this edge. And that would cause 2 adjacent edges, right, to be the same color. So I have to change this now. Let's change that to pink, or to having the label B, right? So B, and this is C. Okay. All right, so that's pink, and then this would be yellow, or equivalently having the label C, and then this would be pink as well, B. And yeah, it looks like this is it. Okay, there you go. So this would correspond to the scheduling. All right, so the edges that are A are the tasks that are colored A, or given this label colored green, or given this label A, would be completed during the first 30-minute interval. So, right, so car wash working on car 1 would happen during the first 30 minutes. Car lift working on car 2 would happen during the first 30 minutes, and the pneumatic wrench working on car 3 would happen during the first 30 minutes. And then during whatever is colored, the edges that are colored pink, or given the label B, will happen during the second 30-minute interval. So car wash working on car 3 will happen during the second 30 minutes. The car lift working on car 1 will happen during the second 30-minute interval, and then the pneumatic wrench working on car 2 will happen during this interval. And lastly, during the last 30-minute interval, yeah, we have here car wash working on car 2, and then car lift working on car 3, and the pneumatic wrench working on car 1. So this may seem a bit trivial too, I might add, just because the number of machines is equal to the number of objects. So it's a little less trivial. So it's just kind of like you're writing permutations in each of these in the scheduling here. It's a little more complicated when these numbers aren't the same. When there are more objects, then machines, specialized machines, or there are more specialized machines than objects. Then this problem of filling in the scheduling becomes harder than finding a minimum edge coloring in the corresponding bipartite graph. All right, so yeah, that ends this video.